All right, this is the Chapter 8, Section 8.1 for video for the online trig class. Now, this is going to tie back to something that was covered in Math 136 specifically in starts in Chapter 3, where you have to learn about, and it ends up that you finish the discussion about inverses in Chapter 5. But you learn what an inverse is in college algebra. Essentially, and I'm going to go to an external website to kind of showcase this with maybe an algebraic equation, because that's usually something that most students recognize more. But say we had the equation y equals x squared. Okay, so that's a parabola. A parabola is, remember, just a quadratic. It has this U shape to it. And we know that it passes the vertical line test, so it is a function. In the previous class, or in 136, you learned that there's also a horizontal line test that tells you if a function is one-to-one. For example, if you draw any horizontal line, if it only crosses it once, then you know that it's a one-to-one function. Whereas notice this parabola does not. It crosses twice. So that makes it not one-to-one. And in fact, it crosses twice everywhere except for at the vertex. And it only has to fail that test once to no longer be one-to-one. So the way a parabola is structured right now, you cannot actually create an inverse. An inverse is when your function is a function, so it passes the vertical line test, and it passes this horizontal line test, which means the function is one-to-one. Each x is unique and each y is unique, whereas here the y's are not unique. They tie to different x's. So the whole reason I wanted to show you this is that what we learn is that if you restrict the domain of your specific function, then you can create an inverse for it. So for example, let's see if this will let me do this on here. If x is greater than 0, no, it will not let me do that. So that's what I wanted to show you was if we were to create the graph and take away this left side, essentially just start at positives with 0 and move to the right. So that would give you something that would be past the vertical line test and past the horizontal line test if this piece over here didn't exist. The way to set that up is to actually set the domain restricted to just values greater than or equal to 0. So that's kind of how this works. We have to sometimes restrict our domain to be able to, and maybe I can show you this way. Yeah, there we go. So if we do this, it's not going to get rid of the graph. But if you were to only plot these points right here, that would give you a parabola that would be on just the right side. So technology is not always the best in the world, but that's what we were shooting for. So just from here on. Then what you note is that the square root of x is going to be a function. So y equals the square root of x. And it is the inverse of this part right here, just the piece that we have the 3 dots on. Now, inverses have a couple cool properties. First of all that's happened is their x's and y's have been swapped. So what we notice is that they reflect over the line y equals x. So again, you have to kind of imagine that this piece over here is gone. This is reflecting across this. Every point here has a reflection somewhere else. Something to note about this. This is the point 2,4. This is the point 4,2. So inverses just have their x's and y's swapped. So that's kind of like a little algebraic review of what an inverse is, what has to exist for you to have an inverse, and just kind of visually showing you this without any trig involved. So now we're going to go back to our notes and we're going to talk about, okay, so does this still apply if you have trig? Because trig, remember these sine, cosine, and tangent, these are functions that we can graph. And we did graph them in the previous unit, or the previous chapter. So here are 4 facts about inverses. So if your function is one-to-one, which we said means it passes the vertical line test and the horizontal line test, it will have an inverse. So that means that if you compose, that's what this symbol means in case you did not take college algebra. If I plug the f function into the inverse, I get x. And if I plug the inverse into the f function, I get x. A good way to see that is to go back to that x squared and square root of x. If you put x squared inside here, then you get that that would be just square root of x squared, which is x. If you put the square root of x in x squared, you get square root of x squared, and the square root and the x, the squared part cancel again. So both of them come out to x. So notice that's what they mean by that. And then the domain of the original is the range of the inverse. That's the x's and y's swapping, which means the range of the original is the domain of the inverse. The graphs are reflections over the line y equals x. I showed you that on the picture. And if a function has an inverse, then the equation of the inverse means that you swap the x's and the y's, and then you take the inverse symbol. That's what this -1 stands for. It's not an exponent. It's the inverse symbol to get this to be in the format so that it is solved for y. Okay, so that's kind of a little side discussion that goes back to college algebra. So what we want to look at is this graph of the sine function. And we want to try to figure out how could we make this one-to-one? For right now, it is not one-to-one. Notice that if I draw any horizontal lines, they're going to hit this graph a ton of times. So it passes the vertical line test, which means it is a function, but it fails the horizontal line test miserably. Just imagine drawing any horizontal line across. It crosses many times. So what we have to figure out is, where could we define the lowest to the highest point of this graph? So what they do, and I'm going to highlight this in blue, is typically we let this be -π/2 to π/2. Notice that every value in the wave for y is represented here. So I go from the lowest possible y value all the way up to the highest possible y value. So every single height of y is represented. If we cut out the rest of the graph, though, everything's only here once. So the way we take the inverse is we restrict the domain. That's how you take the inverse of any function that's not one-to-one. You have to restrict the domain. And then the question becomes, how do you restrict that domain? So we already said this on the picture before. There's lots of different ways I could have gone from the lowest to the highest point. This has kind of been stretched out, by the way. But historically, we use -π/2 to π/2. And the reason we use that is because it keeps us from having extra parts of our graph that would be on the horizontal line test. We still are a function, and every height of y that the sine wave has is represented because it goes from the lowest one up to the highest one with no gaps. Okay, so we have this definition then. Y equals, I don't know why the graph did that. Sorry, the box got stuck underneath there. So y equals sine inverse of x means that x equals sine y. So in your inverse, your x's are -1 to 1, and your y's are -π/2 to π/2. So that's something to remember about inverses. When I have y equals sine x, this is an angle, and this is a ratio, because that's like saying sine of π/3. It's an angle. And this is the ratio, and it would be, what is sine of π/3? Is it 1/2? Is it square root of 3/2? But no matter right now what the value is, if that's just saying that's a ratio. It's a ratio of the sides of a right triangle. When you write this as y equals the inverse, the reason they show you this here is they're showing you x and y has really been swapped. So now the angle is the answer, and the ratio is inside the argument, not ratio. So that gets swapped because it's like the domain and the range have been swapped. Okay? Now, that's why this is now -1 to 1 for x instead of y, because it's been flipped. And this is -π/2 to π/2. And then they kind of show you here how this was the regular wave, so I'm going to do that one in yellow. So this yellow was y equals sine x. This blue one, so that one goes up, is the inverse. Okay, so let's talk about why do we care about this? What can we do with it? Well, sometimes you don't know how to solve a problem that has trig involved unless you look at the other variables. So maybe you, instead of having what is sine of pi over 3, you might be trying to solve 1/2 equals sine x. And you have to figure out, okay, do I know that ratio or do I need to use the inverse to figure it out? So look at mine right here. We're going to actually start out with one that has the inverse already. We want to find the exact value of sine to, inverse of square root of 3 over 2. Notice this is a ratio because we're in the inverse. So we first say let theta equal sine inverse of square root of 3 over 2. Because remember, when you're doing the inverse, the angle is the answer. So by definition, y equals sine inverse of x means x equals sine y, or sine theta equals square root of 3 over 2. So if you want to turn it back into a sine without the inverse symbol, you have to switch the theta and the square root of 3 over 2. So what angle theta has a sine of square root of 3 over 2? And remember, in order for there to be an inverse, the angle we want has to be between negative pi over 2 to pi over 2. And those are usually the ones on, since square root of 3 over 2 is one of those from our unit circle, this chart below just represents all the values between negative pi over 2 to pi over 2 that have ratios that are on the unit circle. So square root of 3 over 2 is in this part down here, square root of 3 over 2, because this one's negative. That does matter. And it looks like that is tied to pi over 3. So because of our restricted domain, we had to stay between negative pi over 2 to pi over 2, and our question was, what angle has a sine value of square root of 3 over 2, and we got pi over 3. Now, of course, there is another place on the unit circle where you get a square root of 3 over 2 and it's positive, and that's cool, but that's not what we were looking for. We had to stay in our restricted domain, otherwise the inverse did not exist. So if you know one of the angles, like you've memorized it, it's one of the unit circle angles, then that's great. You don't need a calculator. Sometimes you will have things that are sine inverse of a number that's not one of our special ratios that we know. For example, and in that case you need a calculator. So the answer to sine inverse of 3/5 is not anywhere on my unit circle for one of my ordered pairs. So that means it's not one of our special ratios for 30, 60, 90 or 45, 45, 90 or even on the quadrants. So we do need to think about where would this be. Okay, so here's what you have to remember. When you're doing sine inverse, you're going to pi over 2 is your max, and negative pi over 2, which is down here since it would be clockwise for negative. This is the region that we're in. So we are over here in either quadrant 1 or quadrant 4. So when dealing with the inverse of sine, these are your two quadrants, okay? 3 over 5 is, remember this is, you have to remember sine is opposite over hypotenuse. So we have to have a positive, opposite's always the vertical distance. So we have to have a positive y. So that means this has to be up in quadrant 1, okay? So this has to be in quadrant 1 because we only have these two choices, and with this to be opposite over hype, the hype is always positive, so that doesn't matter because remember this part, our hypotenuse is always positive in all of our triangles. But this is one possibility for opposite. The other would be down here. Down here the y's would be negative, so that would mean that the fraction would have to be negative. So we are going to be going with quadrant 1. And then we always set our calculator in radian modes if it doesn't have a degree symbol. You assume that you're in radians if there's no degree symbol. So I'm going to go over to my calculator and set this up into radians. And mine, remember, it's a little bit backwards. So here's how I have to do it. I have to enter in the argument first, which is the inside, and then tell it what to do with it. A lot of calculators will let you do the inverse sine first and then type in the 3 over 5. Just depends on your calculator. So I have to type in that I want to do 3 divided by 5, and it'll turn it into a decimal, but I don't ever clear that or do anything with it. And then I see my sine button here. If I go to my shift or my second key, I have my sine inverse. So this gives me, that's not what I wanted. it's giving it to me in a decimal format. So let's hang on just a second. Okay, so we are going to use the decimal because we're approximating here. We're going to go to 4 decimal places, so 0.6435. And that seems really small, but you got to remember this is in radians. So just to give you a frame of reference of what that actually means, remember that pi over 3 is the smallest angle between 0 that we look at on our unit circle. So pi divided by 3 is 1.05. So this is an angle that is smaller than pi over 3. If you look at something smaller than even pi over 3, say pi over 6, sorry, pi over 6 would have been smaller. I was thinking backwards in my head. So remember we had pi over 6, pi over 4, and then pi over 3. So pi over 6 is the smallest angle that we knew on our unit circle. I just said it backwards. So pi 0.5236 is pi over 6. So this is actually a little bit bigger than pi over 6. So this, and if we look at pi over 4, that's 0.78. So this answer that we got, it says that this is somewhere an angle between pi over 6 and pi over 4. So just to kind of give you a frame of reference so that you know that this answer actually makes sense, if you look at the radians and divide pi by the number, you can kind of see that the decimal is in that ballpark. So let's do another one real quick. So the answer to sine inverse of -2/3 will be found in quadrant. Now since this is negative this time, it has to be down here in quadrant 4, because that's the only way you're going to get a negative sign in these 2 quadrants. The positive signs are up here, the negative signs are down here. So if we use our calculator in radian mode again, we'll be able to find an estimate for this. So we take 2, and it's negative, divided by 3. And then I'm going to use my sine inverse button again, and that's negative 0.7297. Okay. And again, these really should be approximates. So we can, if we don't know the specific ratio that's in our inverse, that's when we use the calculator. If the ratio inside here is a half, or square root of 3/2, or square root of 2/2, or a 1, we should know the values that go with those because those are on the unit circle. So it just depends on what they're looking to ask. Okay, so this next part says we're going to use the property of inverse functions to find exact values of composite functions. Combining what is known about composite functions and what is known about sine and its inverse, it can be said that f inverse of f of x, so notice this is that same property up from above, if you have an inverse and a function composed together, if they are truly inverses, which ours are, then the answer is just the x. But the thing about this you have to be careful with is this is x only if you fall within the negative pi over 2 to pi over 2 range. You have to be careful when this is the scenario because excuse me, when you have sine x inside could have any angle going on, okay? But when we take the inverse, we have to make sure we're within the restricted domain. Same thing here, sine and sine inverse, see how they have the inverse inside now? It will be x, but it has to be between -1 and 1, or this doesn't exist. So when the sine x is inside, we're going to be getting an angle for the answer, because remember, that's what the argument is when it's just sine. When the sine inverse is inside the composition, we're going to be getting a value between -1 and 1. So when we do these, we just have to make sure that what we have makes sense. So pi over 12 is between negative pi over 2 and pi over 2. One way to check that is to figure out what pi over 2 is. In case you don't know, you have a calculator. So pi divided by 2 is 1.57. Pi divided by 12 has to be smaller than that to be in that quadrant, and it's 0.26. So you can think of it as that it's smaller than pi over 2, therefore, but it's not so small that it's negative pi over 2. So this definitely falls within our negative pi over 2 to pi over 2 range. So that means that this just is pi over 12. So if these two match and they're inverses of each other, as long as this falls within the restricted domain, it is the answer. So this case knows the inverse is inside, so this is a ratio. Is negative 0.4 between negative 1 and 1? Of course it is. So since those two are both the same and the inverse and the original would kind of cancel each other out, when you compose, you just get this. Now what I mean by cancel each other out is you can kind of think of it this way. Here's the original, here's the inverse. When you compose, you take it one way. So if I have f of f, let's do f, f of f inverse. That means f inverse is my starting point and I map it to f. Well, if you do that, you're going to see that, here's the cool thing about this. So if f goes from, which it does, goes from an angle to a ratio, then f inverse goes from a ratio to an angle. So what this is saying is if I do my regular old sine, I go from an angle to a ratio. Then I plug it into the inverse and I go from that ratio back to that angle. That's why you get the exact answer there. Angle to ratio and then ratio back to angle. So you're just mapping once and then mapping right back. So that's kind of what's going on. So sine inverse and sine of 3 pi over 5. The problem with 3 pi over 5 is that it is bigger than pi over 2. So let's kind of draw this out. So here's pi over 2. Here is negative pi over 2. It's not bigger than pi because to be pi you'd have to be 5 pi over 5 because the 5s would need to cancel. And it looks like it would be somewhere around here. So 3 pi over 5. What you have to consider is what is the sign of sine in this answer, because we actually can still answer this between negative pi over 2 and pi over 2, because something that's interesting about the trig functions, in other words, when you have the angle inside, is that you know your little statement, all science teachers are crazy. Sine is positive, sine is positive, sine is negative, sine is negative. All stands for all the things that are positive in quadrant 1, which is everything. S, remember science, stands for sine's family, the sine and the cosecant. They're positive in this quadrant. Tangent's positive in this quadrant. Cosine and its family members are positive in this quadrant. So sine's negative in these two and positive up here. What's interesting is that every single time you have a sign that is positive, there is another sign on the unit circle somewhere that is also positive. So here's the thing. Whatever this reference angle is here, there's a matching reference angle over here. So how do we figure out what this reference angle is? Well, this is 5 pi over 5. To measure from this baseline up to here, we just subtract. So 5 pi over 5 minus 3 pi over 5. That would be 2 pi over 5. So that means this matching reference angle over here is 2 pi over 5. So the answer to this is actually 2 pi over 5. It's not an exact copy because the original angle they gave me was not between negative pi over 2 to pi over 2. But 2 pi over 5 is the reference angle, the measurement from the x-axis up for that specific angle that they gave me, which means that this over here, where sine is still positive, would be an appropriate solution there. Okay, so here there's two things you have to consider. First of all, is your angle in the quadrant it's supposed to be in? If not, what is the ratio value for that? Is it positive or negative? If it's positive, you need to find in the right quadrants, which for us are the 1 and the 4, because that's where sine inverse is defined. We have to find, is it positive signs on top or positive signs on the bottom? Wherever that exists, that's where you draw that matching triangle and use the 2 pi over 5 as your reference angle. Now, for us, our answer is 2 pi over 5 because that is measured from 0 to this amount. If you were down here, you'd have to tell me it was negative 2 pi over 5 because that would be in the clockwise direction. So Just because this isn't in the negative pi over 2 to pi over 2 doesn't mean we can't find a coterminal angle, or not coterminal, wrong phrase, an angle with a reference angle that's in a quadrant that has the same ratio value as our sine we were originally given. So I hope that's not too confusing. It's just you have to think, if this is the trig value here, is there another place that that same trig value exists? And we see that all the time in the unit circle, because essentially there were just a couple numbers that kept showing up and they just changed signs. All right, so enough about sine. We're going to talk a little bit about cosine for a second. So based on the definition, remember, of a cosine function being one-to-one, we have to look at where would we use, where would we say we need one measurement of our graph. So the typical one that everybody uses is from 0, because that's the highest point on a cosine graph, down to pi, because that gets you every value that y can possibly be, but we don't ever repeat any heights. So notice it's just one continuous line from the highest to the lowest. And notice passes the vertical line test, and just this yellow chunk would pass the horizontal line test. So just like before, how do you find the inverse of cosine? You restrict the domain. And for us, our domain is going to be 0 to pi. So different than sine. Remember, sine was negative pi over 2 to pi over 2. But that makes sense because cosine's the same wave, but it's just been shifted. Okay, so let's look at the definition. This is just showing you the same picture again. Here is the restrictions. The inverse has to have an x between -1 and 1, just like sine had to. But the angle output is between 0 and pi now. So remember, this is our original, this one right here. And in blue, this is the inverse of cosine. Okay? And remember, they are reflecting across that line y equals x. So then we just have to look at a couple examples for cosine, and then we'll spend just a few minutes on tangent. So find the exact value of cosine inverse of negative square root of 2 over 2. Remember, we can say that that would be theta equals that cosine inverse, which means that's a y equals cosine inverse. If you want to just swap that so that you had regular cosine, you switch the variables around. So cosine of theta would be negative square root of 2 over 2. So then we're going to look at our table. You should have these memorized by now, but I know sometimes you have to look at it, especially when you're learning something new. From 0 to pi, because that's where cosine is defined for an inverse, the only place we see a negative square root of 2 over 2 is 3 pi over 4, which is in quadrant 2. So let's look at an example here. We're going to do some more with calculators, because you need to be able to do the ones that are nice values on the unit circle, as well as the ones that are not and need the calculator. So if I want to do cosine inverse of 0.6, first of all, make sure that is between -1 and 1, because you can't plug it in if it's not, because that's the ratio. So 0.6 is going to be, we have to figure out where would that be on our graph. So I always like to draw a little picture right here. So when we're dealing with cosine, here are the two quadrants that are acceptable. Okay. Cosine is positive in this quadrant, but because it's all science teachers are crazy, remember that was my little way to remember that, this is the sine quadrant where sine is positive. So that means over here cosine is negative. So in this scenario, it has to be in quadrant 1 to keep ourselves in our 0 to pi range, but we need a positive ratio for cosine. So we use our calculator in radians, and we will do the inverse cosine of 0.6, which is 0.9273 approximately. Okay. Using a calculator set in radian modes, try to do cosine inverse of 1.8. I'm going to do it first, but then we're going to talk about why it doesn't work, because this does not work. Invalid input. Okay, this is invalid because 1.8 is not between -1 to 1. It's bigger. So remember, because our inverse had to be just a small chunk of the cosine wave, essentially 0 to pi, and plus cosine never gets higher or lower than -1 and 1, we can't plug in a value bigger than -1 or 1, or between them, I should say, into our inverse function. So it is not valid. And then here's the same property we had for the sine before. If you compose cosine, inverse, and cosine, you get just the answer. With the angle one, you can still work with it if it's not 0 to pi, because we can find an identical angle that has the same reference angle information, usually between 0 to pi, and the same sign that we're looking for. But if this part happens, if it's -1 to 1 and this x is, say, a 2, it's just undefined. We can't do anything with it. So that's just a little subtle difference, is that usually you can work with the angle one. That's one where you can think about sines and cosines being positive or negative, and what quadrant would that correlate with. But if this is not between 1 and -1, we can't do anything. So let's look at this. It says find the exact value for the following composite functions, making sure the answers are in the proper domains. So 2 pi over 3 is definitely between 0 and pi, because 3 pi over 3 would be pi. So since that meets the criteria that we need, the answer is just 2 pi over 3. Cosine inverse of cosine of -pi over 5, notice that is not between 0 to pi, but we can find an answer that is. So -pi over 5 is down here, and its reference angle is actually pi over 5, because it's just measuring from the x-axis, which is how we find reference angles. The reference angle will just be positive for us, because we're going to say that we just are measuring this angle distance right here. So remember, the acceptable quadrants to be in are quadrant 2 and quadrant 1. And let's think about what cosine is in each of these. So all science teachers are crazy. Down here, cosine values are positive, because that's the letter right here. This letter represents what's positive in that quadrant. So the other place that cosine comes out positive is up here, because we already talked about how this one is a negative cosine quadrant. So this angle in here being negative does not mean that the actual ratio is going to be negative, because down here your adjacent would be positive, it's in positive x, and your hypotenuse would be positive. So all cosines are positive in quadrant 4. So to make this match, we would need to use pi over 5 reference angle here, because that would still have a cosine ratio that is positive and would match with this angle. So pi over 5 will be our answer. So you just have to make sure you're in the right quadrant for the domain. For this one, because this is between -1 and 1, you can use 0.6 as the answer. Here it's undefined or invalid, because 1.8, we already talked about this one, is not between -1 to 1. Okay, so now we're finally able to look at tangent. So remember, tangent was an interesting graph because it had all these little asymptotes, things at pi over 2, -pi over 2, -pi over 3 pi over 2, -5 pi over 2, 3 pi over 2, pretty much every pi over 2 plus pi or minus pi. So we noticed that those were asymptotes, and that our tangent graph pretty much had to exist in those. Now, it does not have an inverse if you use the whole number line, because you'd be passing through multiple of these little pieces if you did a horizontal line. But if you just restrict yourself to one of these, because they're all matching, then you now see that this is passing the vertical line test, and it would pass the horizontal line test. So again, we end up using -pi over 2 to pi over 2, because that will help us get all the values of tangent, and we will have our one-to-one function. So sine and tangent actually have the same restriction when it comes to inverses. Cosine's the only odd one. It's the 0 to pi. And notice this is different too. For tangent, you can get to any value of y you want. This keeps going down forever. This goes up forever. So our domain may be negative pi over 2 to pi over 2, but our range is all the real numbers. Which means when we flip that and make it the inverse, you can plug in any x you want into the inverse of tangent, but your answer has to pop out between negative pi over 2 to pi over 2. So that is how we deal with tangent. You can plug in any x you want, but the angle has to be in the restricted. And there's the graphs again. I won't go through those since it's a little bit of just overkill and repeating the same things. So we're looking at tan inverse of negative square root of 3 over 3. So remember we said that that means that we're really talking about what angle equaled negative square root of 3 over 3. So from negative pi over 2 to pi over 2, that looks like that is negative pi over 6. So in the unit circle, remember, if you know the ratio, you can find what angle in those two quadrants equals that. Okay, this is something a little bit new. We didn't do this with before because it's just a different skill set. What we want to do now is show you how to find an inverse function. This is something you do learn in a college algebra course, but it's not super difficult. You just have to think through how it's going to set up. So this is really y equals negative 3 cosine x plus 2, because f of x really stands for y. When you want to find an inverse, our first step is to remember what really happens in an inverse. They swap their domains and ranges. So if we physically swap x and y, we have set ourselves up to look at the inverse. The only problem is in any function you want your equation to be solved for y. So we have to actually undo some of the things here. So we're going to subtract 2 over. We're going to divide by negative 3. So y, cosine y, still have our cosine attached to that, equals x minus 2 over negative 3. To get rid of this cosine so that we just have y, we use the idea of composition. If you compose cosine on this side, you have to also apply a cosine inverse to the other side. Now, why would we want to do that? Well, we want to find this inverse. So we're trying to get the y by itself. And remember, composing two functions together, as long as we're staying within our domain, which we are, it says I'm from 0 to pi, so I'm good there, then I know that this is going to give me just y. So then this, I would actually pull that negative out. It's negative, and then x minus 2 on top over 3. So this would be my inverse. And I usually use the notation f inverse to say that this is an inverse of the function I started with. So there we go. It's inverse of cosine, in parentheses, negative x minus 2 over 3. Okay, so now that's my inverse equation. Now they ask me a follow-up question. They say state the range of f and the domain and range of the inverse. Well, we already know the domain of f. They gave us that. Anytime they have something like that attached after a function with an x in the middle, they've given you the domain. So sometimes I like to organize myself in a chart. F inverse, domain, and range. This is 0 to pi. Okay, which means if you remember anything about inverses, we learned this a minute ago when we first defined all this, the domain of the original is the range of the inverse. So I already know the range of this. It's exactly the same except they've swapped for the other function. So that's there. Now to find our range of the original, you have to remember that cosine inside here has to be between -1 to 1. Remember, that's our restriction for the inverse of cosine. The x has to be between -1 to 1. So we set that inside part in between -1 to 1. Because this has a negative here, it might actually have been better to leave it on the bottom. So I'm going to put it back down there just for a second and tell you why. You're going to have to get rid of this fraction to be able to get x in the middle by itself, and that's going to be our goal. So we need to multiply all three sides of this setup by -3. Okay, this would make that +3. Anytime you multiply an inequality by a negative, it flips the direction of the inequality. In this case, this would cancel. We have x minus 2, and this is also going to end up being greater than or equal to because we multiplied by a -3 on this side. Final step is to add 2 everywhere. So this is 5 greater than or equal to x greater than or equal to -1. Now that doesn't read very good, so you can flip the whole thing around as long as everything points to the correct pieces. So it looks like our range is -1 to 5 for our original function, which means it is also the domain of the inverse. So that's interesting, and that's how I like to organize my thoughts. Okay, last example for this section. This was the long section this week. So we want to solve this very weird looking equation for x essentially. Notice that the first two terms have tan inverses in them and everything else doesn't. So you might want to get the tan inverses on one side by themselves, kind of like isolating a variable. So I'm going to leave the tan inverse of x minus 5 tan inverse of x on the left side, and I'm going to add that pi over 3 over. So I have 2 pi over 3 plus pi over 3. On this side, that's going to be 3 pi over 3, which is just pi. Over here, notice they both have tan inverse. You can pull that out. Tan inverse of x. That would leave you, or you could combine them as like terms too. That's another way of thinking of it. That would leave you with 1 minus 5 in this parentheses, which is -4. So tan inverse of x times -4 equals pi. And if we wanted to get that by itself, we would divide over the -4. So negative pi over 4. By the way, like I said here, because these were like terms, I could have just subtracted those and gotten that just as quickly. So there's just two different ways of doing it. Subtracting since they're like terms, or pulling it, the like piece out as a GCF. So whichever made more sense to you, do that. Now we need to get rid of this tan inverse because we don't want this to be tan inverse of x. We want just x. So we need to take the tangent of both sides to be able to do that. So tan and tan inverse are inverses of each other, so we just get x. On this side we have tan of negative pi over 4. And then we would say, okay, and by the way, this is part B from over here. So here's where part B has started. I took the composite rule of both sides. So we just need to figure out what is tan of negative pi over 4. So I'm going to draw a little picture. If we haven't memorized our unit circle yet, remember it's very, very important. Negative pi over 4 is down here. And remember it's a 45, 45, 90. So this is 1, -1, and square root of 2. Remember, tangent is always from the reference angle, and it's opposite over adjacent. So this is going to be -1. All right, so that shows you all the variety of section 8.1. I will be posting 8.2 and 8.3 hopefully shortly. That will continue or finish up the notes for this week.